So all right, and our next speaker is Mateusz Kwasnicki from Wrocław University of Science and Technology, who will speak on the spectral theory for non-self-adjoint Lévy operators in the half plane.
Okay. Thank you very much. So I'm very glad to be here because this talk is actually about what this focus program is about, although perhaps not quite. I mean, there will be a lot of operators in the talk, and there will also be spaces of analytic functions as well, although not in the usual sense, I suppose. And I'm very happy to be here because I can ask specialists and for some advice, maybe. So if you have any ideas about the things that I will be discussing, I'll be happy to have them either right now or later, maybe by email or whatever. Let me start with something very, very, very basic. So consider a self-adjoint operator on a finite dimensional vector space, so just a matrix, square matrix. Then it's well known that we can write it in a diagonal form in the basis of eigenvectors. So there is a complete orthogonal set of eigenvectors that we call phi j. Well, we'll soon move to eigenfunctions. That's why I chose the simple phi. And there are many ways to phrase this. The one that suits us best for the purpose of this talk is in terms of the quadratic form or bilinear form. So usually we would just say that our operator or matrix can be written as a diagonal matrix conjugated by the matrix made of eigenvectors. But the bilinear form can be written in that simple way. So you just take the scalar product of your two favorite functions, u and v, with the eigenvectors, multiply the product of them and lambda j, where lambda j is the eigenvalue, and sum it up. Okay, and now a very classical Hilbert-Schmidt theory tells you that you can do essentially the same for infinite dimensional operators as long as they are self-adjoint and compact. So if we move to compact self-adjoint operators on an infinitely dimensional Hilbert space, essentially nothing changes except that the summation is now infinite, but everything is perfectly convergent, and the picture is essentially the same. And the question is how far we can go with that. So for general self-adjoint operators on an arbitrary Hilbert space, we have the spectral theorem, the classical spectral theorem, which is typically formulated in a rather abstract way in terms of the resolution of identity and the appropriate integral. That doesn't really tell you much about the structure of the operator L unless you know something about the resolution of identity. And it turns out that in some cases, indeed, you can describe this resolution of identity in a way that's kind of familiar. It's a way that is particularly popular in physics, I suppose. The notation is standard there, although it's not really formal always. So what we would like to do is to write the bilinear form corresponding to L in a way that resembles the finite dimensional case or the compact case. So one can hope for something like, okay, this resolution of identity is in fact, this measure value projection is in fact found by integrating against some kind of eigenfunctions phi. But well, these need not be true eigenfunctions. These may be generalized eigenfunctions. So objects which are not in our Hilbert space, but somehow they define some kind of discontinuous functionals on that Hilbert space or something similar. And it turns out that under certain assumptions on the operator, you can indeed do that. So if you start with a self-adjoint Karleman operator on an L2 space, for example, Karleman means that your operator has a nice kernel. So it's given by an integration with respect to the kernel K, which is square integrable for each x. And it's symmetric, of course, because our operator is self-adjoint. So in fact, that gives you a lot of information about the kernel, nice bounds on the kernel. Then it turns out that you can indeed write the bilinear form of L in the form that we just discussed. So you get the sum of eigenvalue times the scalar product of one function with the generalized eigenfunction phi r times a similar object for the other function v, and then sum it up over eigenvalues. But now, instead of summation, you need to integrate. So you get a usually continuous family of generalized eigenfunctions, phi r. These are called generalized because they typically do not belong to the L2 space, so they are not true eigenfunctions. Nevertheless, you can extend the definition of L, I mean, the formula for L, which is written here, the integral formula can be applied to these eigenfunctions. It turns out that in most cases, or under reasonable assumptions, these are true pointwise eigenfunctions of the operator L. So the eigenfunction equation is satisfied in a pointwise sense, and the expression for the operator L is sort of similar. As far as I know, this was proved by Gording in the 1950s and found applications, for example, in the study of Schrödinger operators in the case when the potential is not confining and you can't really get true L2 square integrable eigenfunctions, but you can still write the decompositions of that form. Of course, this is very inexplicit. I mean, unless we know something very informative about operator L, we can't really say what phi r are, but still it gives you some information about the operators. So the question is, actually, what can we do for operators which are not self-adjoint? It's fairly easy to see that if we still consider normal operators, then things do not change much. But let us go beyond the normal case. So if in the finite dimensional case, we still know a lot about non-normal operators, but the best one can do is probably put it in the Jordan normal form. So you have eigenvectors and generalized eigenvectors in a different sense than the one discussed just before. And we cannot get full diagonalization, but something which is very close. If we are lucky, and there are no these generalized eigenvectors, then we can actually write the same eigenvector expansion as before. But this time, we need to use two families of eigenvectors. So one of them is still denoted by phi j, and these are just eigenvectors of L. And let us suppose that the family of eigenvectors is complete, meaning it forms a linearly dense set. Then the same is true for the adjoint for the conjugate of L. And let us call the co-eigenvectors by symbol psi j. And it turns out that the matrix made of psi's, psi1, psi2, and so on, is the conjugate of the inverse of the matrix formed by vectors phi, the eigenvectors of L, phi1, phi2, up to phi n. And the eigenvector expansion looks very similar to what we've seen before, except for we need two different families of eigenvectors. Okay. This is, of course, not always true, but we can hope that if we start with a reasonable operator, that might be true. Well, what happens with compact operators? Well, it's still okay, but not that good as in the self-adjoint case. This theory of compact operators on the Hilbert space due to Friedrichs, and well, we have some substitute for the Jordan normal form. It's not exactly the same, but it's, say, close enough. And if we're lucky, then we can still hope that there are no generalized eigenvectors. They are just pure eigenvectors, and we get a linearly dense family of eigenvectors. And then we expect that the bilinear form can be still written as the sum of eigenvalue times the scalar product of u with co-eigenvector times the scalar product of the eigenvector with phi. Well, here we need a lot of luck because it turns out that there are two problems. Problem number one, I probably mentioned, so problem number one is the existence of phi j and psi j. So we need to assume that these eigenvectors indeed exist, are non-generalized eigenvectors. problem number 2, which is even more severe in some sense, is convergence. So this sum need not converge, even if all the other necessary assumptions are made, because we have no orthogonality here, and this can be sort of oscillating in some sense. Actually, the same applies to Ries's theory. In the general normal form, we can't really hope for series expansion because these series may fail to be convergent. So already here, the situation is bad, at least in the general case, unless we make some assumptions. The question is, what can we say about the general case? But something we would really hope for would be as follows. So if we have an appropriate class of operators on the L2 space, we might expect that we have a generalized eigenfunction expansion, GE in short, in the very similar form as before. So it's a kind of mixture of the discrete case from the non-symmetric matrices and the continuous case from the self-adjoint operators. So what we would expect is that the bilinear form of L is given again by the integral over appropriate measure space Z of eigenvalue lambda r times these are the same guys, the scalar product of U with psi r and the scalar product of phi r with V, where psi r and phi r are generalized eigenfunctions and co-eigenfunctions. So in this Karleman operator setting, we would expect that these are pointwise eigenfunctions and co-eigenfunctions of the operators L and the adjoint of L. And once again, these are not necessarily in L2. We expect they will not belong to L2. So maybe we should not really use the notation for the scalar product, but I hope it's clear. It's just the integration of the product with the conjugate on the second term. But that might be too optimistic. And it turns out that even though in the end we get the result we wanted, this is too optimistic. It's not that good, as you will see soon. So that was very general. In fact, I don't really like to consider very general operators. I have a very concrete motivation coming from probability. So let me speak a little bit about probabilistic motivations behind the scene. So I'm a probabilist, although many people in probability will disagree with that. They will say I'm an analyst. But I like speaking probabilistic language, which is perhaps not very accessible to analysts. So this will be very basic and very limited without any details, but just to give you a hint of what's behind that. So first consider a Markov chain. So the process which jumps between a finite number of states, which we number from 1 to capital N, little n. And it jumps at random times. So it wakes an exponential amount of time, exponentially distributed amount of time at a given state. And then it makes a random jump according to some rule. And that rule only depends on where the process is. That's called Markov property. So it doesn't really remember what happened in the past. It just takes care about what state it is in. And these jumping rates between different states will be denoted by nu subscript ij. So for example, nu 1, 2 is the rate at which it jumps from state 1 to state 2. And in general, these need not be symmetric. So for example, it jumps from 2 to 1 can be forbidden, even though there are jumps from 1 to 2. And this process has transition probabilities, which means numbers tell you what is the probability that it moves in time t from state 1 to state 7, for example. And the matrix of transition probabilities forms the transition operator, which will be denoted by pt. In terms of analytical terms, pt is just the exponential, matrix exponential of t times L. So that forms a semi-group of matrices. And we can study spectral theory of these matrices, for example. So if we do that, then it's fairly easy to see that, at least in the symmetric case, we get a full diagonalization of the matrix L. and the exponential of t times L has the same set of eigenvectors. What changes are the eigenvalues. Now let us denote the eigenvalues of L by minus lambda j. Then the eigenvalues of pt are exponentials of minus t times lambda j, of course. We put the minus sign to have everything non-negative, because in that case, the operator L is negative definite, so it's convenient to have lambda positive. So that's why we put the minus sign. Okay, so that's in the symmetric case when the transition rates are the same in both directions, unlike in the previous picture. Okay. Now let's move to infinite dimensional case. So not only we consider infinitely many states, but in fact we consider a continuous state space. So the most famous example here is the Brownian motion. So consider a Brownian motion run in a certain domain until it exits that domain. So if you followed Krzysztof Bogdan's talk 1 hour ago, you certainly know well certainly have seen at least what this process is. And this process corresponds to the Laplace operator. So if you don't like probability at all, and just think, we consider the Laplace operator with Dirichlet boundary conditions in a domain. Okay. Another example is jump type process, which moves in a very similar way, but instead of continuous motion, we have a lot of jumps. Jumps occurring at random rates, at random size, and so on. Analytically speaking, this corresponds to a non-local operator, which is the integral of the difference of u of y and u of x times the intensity of jumps. So that's essentially very similar to what we've seen before. In the previous slide, in the Dirichlet case, the generator of a Markov chain was a discrete operator of the same form. If you looked at the matrix, it's exactly of the same form. We could put it into two different integrals, and the other one would not depend on u would not depend on y. We can do that if mu is a finite kernel, but typically we consider infinite kernels, which means that our process makes infinitely many jumps in every finite interval of time. And in this case, you can't really separate this into two integrals. And you can show that indeed these operators are well defined on appropriate function spaces. And in fact, they are negative definite, which means that they generate a semi-group of operators on a appropriate L2 space. And we'll denote these exponentials of the semi-group by PT. Probabilistically, these are again transition operators, which tell you the kernel of that operator, which we'll denote by PT xy, tells you what is the probability of moving from x to y, essentially, or what's the probability density of moving from x to y in time t. And in general, that's a sub-probability kernel because the process can die out by hitting the boundary or exiting the set, not necessarily into the boundary in the non-local case. Okay, so these are the operators that I'm interested in, and I'd like to know as much as possible about these operators. Now, if we assume that these are, well, L is never compact because it's usually an unbounded operator. Never is maybe an overstatement, but it's rarely compact. Typically, it's an unbounded operator, but the semi-group is a semi-group of contractions, and if we're lucky, these are compact operators. So if we're in a symmetric setting, these are compact self-adjoint operators. We can apply what we discussed in the first section of the talk to them. And it turns out that we get an eigenfunction expansion with possibly infinitely many terms, but it's perfectly well behaved. Okay, so if our processes live in a space of finite size, more or less, very informally speaking, this will typically be the case. So, for example, if you consider the Brownian motion in a finite domain, you will have a complete orthonormal set of eigenfunctions phi j and an expansion written in that slide. However, if the domain becomes infinite, unbounded, things may change. In this case, it turns out that these transition operators, PT, are Karleman operators. So we can apply Gatour's result, which Gatour used the results of guarding for Karleman operators to write down eigenfunction expansion of the operator, the generator of the Markov process and the semi-group of the Markov process. So we get indeed the generalized eigenfunction expansion of both guys under appropriate assumptions. And that's essentially what was used to study processes related to Schrödinger operators in the 80s, for example. Okay, but that's what we know about symmetric processes. And I'm also interested in non-symmetric case. So for non-symmetric processes, we can hope that we again get compact operators. And in this case, we don't really know much. We know nothing more than Ries's theory tells us. And again, if in the optimistic scenario, we might expect to get the eigenfunction expansion as in the symmetric case with eigenfunctions phi j and co-eigenfunctions psi j. But again, nothing is known about convergence of these kind of series in general. And examples can be constructed in which these series are not convergent, for example. What I'd like to do is actually to move to the more general situation when the spectrum is no longer discrete. The operators PT are not compact. And in this general case, well, that's essentially nothing is known. So I can only throw a sad smile here on the remaining part of the slide because it's completely unexplored land. So let us have a look at the toy example. The simplest possible example here is perhaps the Laplace operator, or maybe even the Laplace operator in one dimension. So consider that first the Laplace operator in full space. One-dimensional Laplace operator is just the second derivative operator. This corresponds to the Brownian motion. So if there are probability people around us, here's the picture for you. So we consider just the usual Brownian motion. Now we can use a Planck-Rhodes formula to write the bilinear form of L. We know that the Fourier transform of the second derivative is minus psi square times the Fourier transform of U. So we get this nice expression for the bilinear form of L. And it turns out that this is precisely the generalized eigenfunction expansion of our operator. Of course, we don't usually see this formula in that way, but that fits the picture perfectly. If we define phi psi of x as the exponential of I psi x, then here we see the Fourier transform of U, which is just the scalar product of U with psi psi. Okay, it's not the scalar product because phi psi is not square integrable, but it's just the integral of U times phi psi conjugate. And similarly for the conjugate of the Fourier transform, that can be written in precisely that way that we expected. It's not really a surprise. This is a self-adjoint operator. So we know that the Tour's theory applies, and it's no surprise that we can cast it in that form. But let's have a look at a little bit more complicated example. Sorry, before we do that, I want to make one remark about generalized eigenfunction expansion. Even in this simplest possible setting, the generalized eigenfunction expansion is not unique because we can write the integral from the previous slide and then change the contour of integration to essentially any curve that, informally speaking, goes from minus infinity to plus infinity. So for example, this contour gamma fits perfectly the picture. And in this case, we get essentially the same generalized eigenfunction expansion. But this time we get different eigenfunctions and co-eigenfunctions. The eigenfunctions are given by the same expression. The co-eigenfunctions have a conjugate of xi in the exponent. But still, this fits the expected picture for non-symmetric operators. This already tells us that there are essential problems with that. For example, it's not always clear which choice of the families of eigenfunctions, co-eigenfunctions is the best one. In this picture, in this case, it's clear that not changing the contour at all is the best what one can do, because otherwise we get, for example, unbounded eigenfunctions or co-eigenfunctions. It's always to have these guys as well behaved as possible. So it's in some sense optimal to stay on the real line here. But that already shows us that we should expect some problems. And now let's move to a little bit more complicated example. Let's add a linear term to our operator. So instead of just the Laplace operator, we add a constant times the first order operator, the derivative of u will still remain in dimension 1. We can do essentially the same as before. So we can write the Plancher's formula and observe that again, we get the same family of eigenfunctions and co-eigenfunctions. So we get the usual generalized eigenfunction expansion, except that the multiplier now is complex valued because the operator is not really self-adjoint, but it's still a normal operator. So it still works as expected. Just the eigenvalues are complex. Or to put it in different words, the operator L is equivalent to multiplication operator with multiplier, which is no longer real valued, as is the case for self-adjoint operators. It's a complex valued operator. Okay, and again, we can deform the contour of integration slightly. And in this case, it's not really clear what is the optimal choice of the contour of integration. We again get the same family of eigenfunctions and co-eigenfunctions for complex psi. So there's an extra conjugate here. We have the same flexibility for the choice of the contour gamma. And there are two natural choices. One of them is just the real line as expected. In this case, we get bounded eigenfunctions and co-eigenfunctions. And actually they are equal to each other, which is very symmetric and nice. But there's a different choice, which can also be argued to be natural. The other one is a horizontal line at the level bi. So that's the other line in the picture here. And if we write down these expressions carefully, it turns out that everything can be written in terms of real valued expressions. They're no longer complex numbers here. Especially when it comes from probability, you don't expect complex numbers appearing in expressions that describe the behavior of the process or things related to the process. It's really preferable to have everything real valued. So that's a good criterion, perhaps, to expect that, say, both psi and phi are real valued, that the eigenvalue is also real, and so on. Well, it's not really an eigenvalue anymore, but that multiplier is still real. And it turns out that, well, I mean, as written, it's not really real valued, but if you write down and expand this, you can divide this expression, this product, into two real valued objects. Okay, and now let's make our toy example still a little bit harder, but explicit enough to do the calculations by hand. So now consider the Brownian motion with drift, which starts at a certain point, the x, and it only lives until it hits the boundary. So if the drift is positive, it goes upwards. There's a positive probability that it will never see the boundary, and we're okay with that. But there's still a positive probability that it will eventually hit the boundary and die out. Analytically speaking, this is the same operator, but now considered only in the interval 0 infinity in the positive half line, with an additional boundary condition imposed at 0. So we require u of 0 to be equal to 0. Now things are a little bit more complicated because our functions exponential I psi x are not equal to 0 at 0. So we need to work a little bit harder to find eigenfunctions. And the eigenvalue problem, which is written here, with eigenvalue of that form for to make the notation simpler, can be found explicitly, and it's written here. It's the guy that we know well, minus a similar object with psi replaced by minus psi plus 2ib. If b is 0, then this is simply equal to 2i sine of psi x. So that in the symmetric case, this leads to the Fourier sine transform, which is essentially the same object as the usual Fourier transform for odd functions. But when b is non-zero, this is no longer the case. So this is for b equal to 0. Okay, so we get a family of eigenfunctions, pointwise eigenfunctions, of course, because they are not even bounded, which take value 0 at 0, so they satisfy the Dirichlet boundary condition, and we can see whether they give us the generalized eigenfunction expansion. It turns out that they do. It's a very short calculation, but I don't really want to present it here. It turns out that indeed you get exactly the same formula as before. Oh, sorry. Exactly the same formula as before, with a contour gamma, which is no longer going from minus infinity to plus infinity. It starts somewhere on the imaginary axis and then goes to plus infinity. The constant changed a little bit. This kind of sort of technical differences. And the eigenfunction is given by the formula from the previous slide. The co-eigenfunction is a little bit different. We have complex conjugate of psi and a minus sign in the exponent in the other term. And note that in this case, the choice of the appropriate contour is clear again. The right one is the one that starts at the level B and is horizontal. And let me explain briefly why is this natural. This is natural because, well, these functions psi and psi are never bounded here because of the two exponentials present here. Okay, one of them is not bounded, the other one is, or maybe. But if you look at the one that is certainly not bounded, it will grow exponentially. And in order to make this growth as slow as possible, you should choose points with imaginary part equal to B, to B. So that makes these eigenfunctions, co-eigenfunctions in some sense as small as possible. And at the same time, this leads to expressions that are real valued. So in some sense, both our criteria are satisfied by this choice. Okay. So that's a toy example because everything could be calculated explicitly. And if you look at it carefully, you will see that adding this linear term does not really change much because you can compensate that by multiplying by an appropriate exponential. So it's all the same. Everything here is the same story all over again. But nevertheless, it turns out that this is the right approach to more general operators that arise from probability. So our goal is to do a similar study for generators of other Markov processes. And what can this be used for so far is to express the heat kernel in terms of some kind of explicit objects. There's a plus here that I will explain why in a minute. And another application is to study what's called supremum or infimum functional, which is essentially the same problem if you look at it carefully. Well, the infimum functional is just the infimum, the smallest value of the process x up to time t. If you start the process at a point x and then let it go for time t and see if it did not cross the level 0 until that time, then you just look at the infimum and check whether it's positive. So you can instead start the process at 0 and see whether the infimum is greater than minus x. So these two problems are, that one and that one are really the same problems and phrased in a different way. So that's my original motivation. I wanted to see whether we can find expressions for the supremum and infimum functionals for a certain class of processes. These processes are Lévy processes. You've heard about them in the previous talk if you followed it. We will only consider one-dimensional objects. One-dimensional Lévy process is just a translation invariant Markov process in R. Its generator will be called the Lévy operator. Sorry for the typo. A Lévy operator is just a generator of that. If you don't like probability, then here's a formula for that one. That may have a linear term, a quadratic term, a second order term, and also a non-local term with a kernel which is translation invariant. And there's some compensation here that I don't really care much about. So it's essentially the same object as before, but with some extra stuff in it to make it as general as possible. Okay, now such operators are of course translation invariant and hence Fourier multipliers, the symbol will be denoted by minus f of psi. So f from now on will stand for the symbol of L. And the symbol is given by the Lévy-Khinchine formula, roughly speaking. So you get the Fourier transform of the second order derivative, the first order derivative, and the non-local guy, which I will not really discuss much. And the transition operators, or the heat kernel, are also Fourier multipliers with the symbol exponential of minus t f of psi. Now I will consider a particular class of one-dimensional Lévy processes. These are called Lévy processes with completely monotone jumps. So we'll assume that the kernel nu of the non-local part is a completely monotone function on the positive axis and the mirror image of a completely monotone function on the negative axis. A completely monotone function is something that is decreasing, but convex. It's positive, decreasing, convex, and the third derivative is again negative, the fourth is positive, and so on. Equivalently, by Bernstein's theorem, these are precisely Laplace transforms of negative measures. So we assume that both nu of z and nu of minus z are completely monotone. That will be a standing assumption throughout the rest of the talk. The characteristic functions of these class of processes, so the functions f, which are full symbols of the corresponding operator L, have a very particular analytic structure. Namely, they turn out to extend to the right complex half plane and satisfy that property. The real value of f divided by psi is non-negative. That means that f over psi is a Van Lina peak function. But it's actually convenient to have a name for that. And since this was studied by Rogers in 1983, I suggest that we call these kind of functions Rogers functions for short. And it turns out that these two conditions are equivalent. So a Lévy process has completely monotone jumps if the symbol f extends to a Rogers function. So has this property. So analytically, we'll consider Fourier multipliers with particular symbols. Now let me define the spine of Rogers function. So we have this analytic extension. It turns out that there's a unique curve along which it takes real values. These values are necessarily positive, it's easy to see, but it's not trivial to see what are the properties of that line. It turns out that these lines intersect circles centered at the origin in at most one point. So it kind of goes further and further away from the origin. It can wind up a little bit, so it's not a graph of function, but it can be parametrized as zeta r, where zeta r has modulus r. And r is in some set. It's not necessarily the entire half-line. It can be a smaller half-line or even a finite interval or more complicated things. It's fairly intuitive that these parameterizations zeta r is nice. I was able to prove that it's Helder continuous with exponent 130, but actually a nice conjecture is that it's 1/2 Helder continuous. But I have no idea how one would prove that kind of statement. The values of f along that curve are 1/3 Helder continuous, and that's optimal. As simple examples show. Of course, inside the half-line, these are smooth, even analytic. The question is, how do they behave near the boundary? And these irregularities, of course, a statement about boundary regularity of these guys. And that's actually one of the crucial points in the development of the theorem. Now, let me show you just a few spines. So if you consider the Brownian motion with drift, or the second order operator, the Laplace operator plus first order term, then the spine is just horizontal. And that's the optimal choice for the corresponding eigenfunction expansion. And what we call stable case. So if we consider stable Lévy processes, then the corresponding Fourier multiplier is just a power function multiplied by a complex constant A in the right half plane. It's different in the left half plane. And the spine is, well, again, straight line. If you add two operators of that form, one of them will dominate locally and the other one will dominate globally. So the spine will be more complicated. In general, it's difficult to see what the spine is for a given function that requires solving sometimes complex equations. But you can work with some meromorphic functions to construct examples that show, for example, that 1,3 Helder regularity of lambda f of lambda r is optimal. So for meromorphic Rogers functions, you can really see what the spine may look like. It can be a semicircle or a finite arc. It can be the union of a number of arcs like that, arranged in a way so that these all conditions are satisfied. It can have more complicated singularities on the boundary. It can get arbitrarily close to the boundary, can get tangent to the boundary. The behavior can be complicated. And actually, you can really write down the expressions for Rogers functions which have that kind of spines. Okay, and I will consider precisely these operators restricted to the half line. So imagine that we put a Dirichlet boundary condition, not only at 0, but also in the entire negative half line, because we have a local operator. Or to put differently, we restrict the operator L to the positive half line. So the bilinear form of L plus, that's the reason the plus appeared in the previous slides. The bilinear form corresponding to that operator is just the integral of Lu times V, but the integral only from 0 to infinity. And this bilinear form corresponds to a unique operator that generates a semi-group of operators PT plus, living also in the half-line. And analytically, the construction is, I think, a little bit complicated, but probabilistically, it's again the same story. You just take the process, the Lévy process corresponding to L, and you kill it as soon as it goes below 0. Okay, I have 8 minutes left and a few slides to show. So here are the results. I made a very long introduction, hoping that I will at least explain what my motivation is and why I'm interested in that kind of operators and why I consider these expressions natural. So the first result is actually 10 years old. With Jacek Małecki and Michał Rysnar, we managed to prove the generalized eigenfunction expansion in the symmetric case. So for symmetric Lévy processes with completely monotone jumps or the corresponding Lévy operators, we have precisely the usual, the expected generalized eigenfunction expansion. And the eigenfunctions here are given sort of explicitly. As soon as you know the analytic extension of F, you can really write down the formula for that. And the formula turns out to be very regular. So you get a sine term plus a correction term. The correction is a completely monotone function. So it decays very fast at infinity. And it makes a sine term disappear at 0 as well, in some sense. So here is a graph. It tells much more than any expression. You take a shifted sine, you subtract the correction to get the blue curve. So that's the eigenfunction, the blue curve. Okay. And since then, I was really thinking about what happens in the non-symmetric case, whether one can get a similar picture. I was aware of the result for the Brownian motion of drift, but nothing else really. Turns out that the answer is yes. So here's the theorem. The theorem tells you that for a possibly non-symmetric Lévy process with completely monotone jumps, satisfying a mild assumption on the spine. So it tells you that the spine avoids this yellow region here and there. So at infinity, the argument of a point lying on spine does not get close to plus or minus pi over 2. And for an appropriate class of functions U and V, we come to these spaces of analytic functions now. We have the generalized eigenfunction expansion in the form that I just discussed throughout the rest of the entire talk up to now. And again, phi and psi are given explicitly. So you recognize the sine term and the correction term, which are, again, of the same form. But what is striking here is that you get an extra exponential term here. And the exponential term depends on R, so it can get really huge. So the usual picture of phi and psi is here. So if, say, the imaginary part of zeta is positive, then phi will behave like a sine for a certain initial amount of time, and then it will converge to the correction. Actually, the correction will dominate the sine term, sine exponential term. So it will be eventually positive. And on the other hand, the function phi, the function psi, will become totally wild at infinity. It will grow exponentially fast, and the rate of growth will typically increase with the r. So if you think about it, it's not really clear why the right-hand side should be convergent. Actually, it's not. Quite often, it's not. So if you consider, for example, the power case, it's just one of the simplest possible. Then the picture is really what it looks like. So phi decays exponentially. I should write the correction term which dominates here. But psi grows exponentially, which means that although the scalar product of phi and v will be bounded as a function of r, the other term will grow exponentially fast with r. So that guy grows exponentially fast. The question is whether lambda grows also at least at a linear rate. It does when alpha is greater than 1, but it does not when alpha is less than 1. So that means that for alpha less than 1, this is not really convergent for u and v, which are compactly supported. And that's why we need the class of admissible functions. Admissible functions are precisely those functions for which we can prove that these integral expressions converge. And once we know they do, we can show that the result is true. So a function is admissible if it extends analytically to a sufficiently large sector, essentially to the right half plane minus epsilon, and it satisfies a very, very tough bound in that region. So it must decay super exponentially in that region. That's used to figure out that the Laplace transform is an entire function which has a very good bound, except for a tiny sector around the negative half axis. Well, actually, what we need is that the Fourier transform extends analytically to a well-behaved function, except for the region when we know that the contour of integration gamma only touches finitely many times, right? So if you remember our condition on gamma, gamma was to avoid, well, that region far enough from the origin and a similar region downstairs. That's because we will use a Fourier transform of u and the conjugate of the Fourier transform of v, which will have different behavior. Okay, so these assumptions, this explains why we need these assumptions. And actually, it turns out that under these assumptions, the result is true. It should be possible to use Fubini's theorem and some kind of density argument to show the expression for the kernel function. So we expect that the kernel is given by, well, a very similar expression without integration against u and v. So we kind of disintegrate with respect to u and v. And that's indeed the case, but we need more regularity here. In addition to the condition that we've already seen, that the spine remains away from the imaginary axis at infinity, we need some additional growth rate for lambda r. So that looks very technical. I will not get into details, but you see the same constant beta here and there. So one can compensate for the other. And it turns out that it looks close to optimal, but it's not really optimal when you think about fractional derivatives. And that will become clear in the next slide. We also have a corollary about the supreme functional, but just to make this thing simpler, I did not write it here. That requires even more technical assumptions for some reason, for reasons that are really not clear to me. So as I mentioned, the case of the Laplace operator and the Laplace operator plus linear term, these are really classical and very old. Perhaps they have not been stated in that way, but it's very standard. For symmetric operators L, this result is given in two papers from 2011 and 13. And there's another paper that I did not mention, which deals with fractional derivatives, or if you come from the word probability, with stable Lévy processes. So symbols of that form, there should be no mod here. Sorry for that. So maybe I'll try to clear it. I only have a white eraser, sorry for that. Okay, that's a paper that I wrote with Alexei Kuznetsov in 2018. And in that paper, we were able to handle all alpha greater than 1. The result that I've shown you 2 slides ago only handles alpha greater than 3/2, 3/2. And also some particular cases when alpha is between 1 and 3/2. That's why I say it's not really optimal in a sense. But in that paper, we use some special structure of these function f. Everything becomes one-dimensional here. There are not two variables, but just a single one due to scaling. And things are much simplified by that. And for the general L, this is given in 2 papers. One of them is not really yet available. I hope it will be available in a few weeks, but I said the same thing 1 year ago, so don't really trust me. The work is done. What I need to do is just to write down some examples and discussion. So if you have any remarks related to that, please do let me know. I'll be happy to share the draft of the paper with you and perhaps see what's related in the literature. I'm particularly interested in this class of test functions. Of course, it's not a Hilbert space. It's probably not the optimal choice. I've never worked with spaces like that. So if you have any ideas, I'll be happy to hear them. And in my last slide, let me just mention very briefly what's inside the proof. So what we start with is an integral expression for the triple Laplace transform of the heat kernel of Pt plus with respect to t, x, and y. That's known since 50s, essentially, due to Baxter and Donsker in different forms. This was also found by Frischted and Peczewski-Rogozin. And then what we do is just invert the Laplace transform. But that's very technical and requires a lot of contour deformations. For example, we need to deform the real line to or half line to the contour gamma, the spine of the Rogers function. So we need a lot of estimates along that contour. We need a lot of regularity of that contour, the Helder regularity, for example, to know that it's rectifiable. So that really plenty technical estimates needed here. And we need to know that the spine is regular enough. I already mentioned that. That's related to the question of what is the boundary regularity of level lines of harmonic functions in the plane near the boundary. Inside the domain, they are analytic, but near the boundary, they can get rough. And some additional structure is needed in order to get what we need. And finally, at some point, Hilbert transform appears, and we need to know that it acts nicely on Helder continuous functions. That's another reason we need Helder continuity of everything. My time is up, so I'll stop here. Thank you very much for your attention. If you're curious what's in the last slide, it's just empty so that I can write something on that, answering your questions. Thank you for your attention.
Thank you, Mateusz, for a very interesting talk. Now we have time for questions. Mateusz, sorry, very naive question, but so is it true that, well, if coefficients are variables, so let's say they're nice, but variable, then does it work to some extent?
So if you drop translation invariance, everything breaks down. Even in the self-adjoint case, there's essentially no way to handle that, I suppose. That really hinges on translation invariance. So my understanding is that variable coefficient means that it's no longer a function of a difference of y and x, but you really get things dependent on x. That's of course a very natural question, but I have absolutely no idea how one can even deal with very regular cases when everything depends on x.
Okay.
May I ask a question? Maybe we need to somehow emphasize what are the applications of those eigenfunctions. I'm not sure if this was clear because I somehow maybe lost that.
Yeah, so I mentioned here that, well, my motivations are probabilistic, and what I'm interested in is, what I was originally interested in is some kind of expression that's suitable for whatever, numerical calculations or finding out the estimates or asymptotic expansions of the distribution of the supreme and infimum functionals. So that's here, we have an expression that's, at least in the symmetric case, was successfully used to find out some information about these objects. So one can expect that in the non-symmetric case, this will be very similar. And that's my original motivation. When it comes to other applications, I'm not really aware, but actually I find it personally very interesting to see to what extent one can develop this theory of generalized eigenfunction expansions for non-normal operators. As far as I know, there are no general results. There are some results for paranormal operators when you kind of embed your operator in a larger space where it has some kind of normality. But this does not seem to be the case here. So it's kind of new direction of that may be explored further, perhaps with methods that I'm not aware of, or maybe in directions that I'm not aware of. So I think that's not maybe application, but that's one possible thing to do with it at a later stage.
So if we look at this, as we see this formula G, so that's a representation of a heat kernel, of the Dirichlet heat kernel, right? For the half-line. As an integral, that's always good, especially if the integrand is non-negative, but here it's not.
Of course, it's an oscillatory integral, and you get the exponential term, which is very, very wild. So in the theorem, move to the theorem, if we speak about the heat kernel, then we need to assume really that lambda r, these eigenvalues, so to say, grow fast enough to compensate for the exponential growth of one of the factors here. So it's not really something that it's ready to use out of the box. You need to do something with it in order to get some kind of asymptotic expansions. But it's on the other hand, it's fairly straightforward what one can do with it. So if you look at it, it's not that. I mean, in particular cases, you can really use it to find some kind of asymptotic expansions, for example, in certain regimes.
I'm always impressed by the fact that somehow the Dirichlet heat kernel should be representable by some expression, like, let's say, derivative of the heat kernel, right? So that's similar and may be very useful here. But both there and here, you have oscillations. Oh, that's fine.
Yeah, I mean, even for the Brownian motion in a finite interval, you have oscillations. You can't help it.
Okay. Thank you.
Other questions? If not, then let's thank our speaker. Thank you.
Thanks a lot.
See you tomorrow.
Yep. Bye-bye.